Welcome to an exploration of how fluids behave differently at the nanoscale, where classical physics meets its limits. In nanochannels, fluids exhibit surprising behavior. Instead of sticking to walls, they slip and slide, fundamentally changing how we understand fluid flow. Let's start by understanding the classical assumption that has dominated fluid mechanics for centuries. For over 200 years, scientists assumed that when a fluid contacts a solid wall, the fluid velocity at that exact point is zero. This is called the no-slip condition. This diagram shows the classical no-slip boundary condition. At the wall, the fluid velocity is exactly zero, then gradually increases as you move away from the wall, creating a velocity profile. Mathematically, we write this as v at the wall equals zero. This seems intuitive, right? This no-slip condition works extremely well for everyday flows. Water in pipes, blood in arteries, oil in engines. The no-slip condition accurately predicts their behavior. But here's the fascinating question. What happens when we shrink our channels down to nanometer scales? Does this assumption still hold? At the nanoscale, something remarkable happens that defies our classical understanding. In nanochannels, experiments reveal that the fluid doesn't stop at the wall. Instead, there's a non-zero velocity right at the boundary. The fluid actually slips along the surface. Careful experiments in channels just tens of nanometers wide consistently show that fluids slide at the walls rather than sticking to them. So how do we measure and quantify this slip? Scientists introduced a parameter called the slip length. The slip length is the key parameter that tells us how much the fluid slips at the boundary. The slip length b is defined as the wall velocity divided by the velocity gradient at the wall. This tells us how far into the wall we would need to extrapolate to reach zero velocity. Here's a visualization of slip length. The velocity profile is linear near the wall. If we extrapolate this line into the wall, the distance where it would hit zero is the slip length b. In nanochannels, typical slip lengths range from 10 to 100 nanometers. This might sound tiny, but when your channel is only 50 nanometers wide, a slip length of 20 nanometers is huge. To put this in perspective, a single water molecule is about 0.3 nanometers across, so a slip length of 100 nanometers represents about 300 molecular diameters. Now let's understand the physical mechanisms behind this slip phenomenon. At the molecular level, slip occurs because the interaction between fluid molecules and the wall is weaker than the interaction between fluid molecules themselves. Hydrophobic surfaces, which repel water, show much larger slip lengths. The water molecules prefer to interact with each other rather than stick to the surface. Surface roughness at the nanoscale can either reduce slip by creating friction or enhance it by trapping air pockets that the liquid flows over. Temperature also plays a role. Higher temperatures increase molecular motion, which can change the strength of surface interactions and thus affect slip length. Let's formalize this with the mathematical framework that describes slip boundary conditions. The slip boundary condition states that the velocity at the wall equals the slip length times the velocity gradient at the wall. This replaces the classical no-slip condition. Notice that when the slip length b equals 0, we recover the classical no-slip condition where velocity at the wall is 0. At the other extreme, if b approaches infinity, we get perfect slip where there's no friction at the wall at all. The friction force in a channel equals the viscosity mu times the area A times velocity v divided by channel height h. But with slip, we must modify this. The friction force becomes mu a times versus divided by h plus 2b, where the factor of 2 accounts for slip at both walls. The slip boundary condition dramatically changes how much fluid can flow through a nanochannel. In classical fluid mechanics, the Poisson equation tells us the flow rate through a channel without slip. The classical flow rate Q0 equals h cubed times width w times pressure difference divided by 12 mu L, where h is height, mu is viscosity, and L is length. Now let's see what happens when we include the slip boundary condition. The flow rate with slip equals the classical flow rate times 1 plus 6 b over h. This is the key equation showing slip enhancement. Let's work through a concrete numerical example to see how significant this effect can be. Imagine we have a nanochannel that's 50 nanometers tall. This is typical for nanofluidic devices. Suppose measurements show a slip length of 20 nanometers, which is reasonable for a hydrophobic surface. The enhancement factor is 1 plus 6 times 20 divided by 50, which equals 1 plus 2.4, giving us 3.4. This means the flow rate increases by 240%. The fluid flows more than 3 times faster than classical theory predicts. This bar chart dramatically shows the difference. The classical prediction is dwarfed by the actual flow rate when slip is accounted for. Here's a crucial insight. The slip effect becomes more important as channels get smaller. The key parameter is the ratio of slip length to channel height. As channels shrink, this ratio grows, making slip increasingly important. This graph shows flow enhancement versus channel height for a fixed slip length of 20 nanometers. As the channel shrinks, the enhancement grows dramatically. When the channel height equals the slip length at 20 nanometers, the flow is enhanced by a factor of 7. Even at 100 nanometers, the enhancement is still 2.2 times the classical prediction. These slip effects have profound implications for nanotechnology and applications. In drug delivery systems, slip can enable faster transport of therapeutic molecules through nanoporous membranes, improving treatment efficiency. For water desalination, slip effects can dramatically increase water flux through nanofiltration membranes while maintaining salt rejection. In lab-on-chip devices, accounting for slip means you can pump fluids with less power, enabling more efficient portable diagnostic systems. In energy applications, from fuel cells to hydraulic fracturing, slip effects can significantly alter performance predictions. Let's quantify exactly how much slip reduces friction in these systems. The friction coefficient F is defined as the friction force divided by half RHO v² times area, the standard definition from fluid mechanics. With slip, the friction coefficient becomes the classical friction coefficient times H divided by H plus 2B. This shows friction reduction directly. Using our previous example with H equals 50 nanometers and B equals 20 nanometers. The friction coefficient with slip is only 0.56 times the classical value, meaning friction is reduced by 44%. This 44% friction reduction is enormous for applications requiring efficient fluid transport at the nanoscale. Temperature plays a fascinating role in modulating slip length through several mechanisms. As temperature rises, molecules move faster, which affects how they interact with surfaces. Viscosity decreases with temperature following an Arrhenius-type relationship, which indirectly affects slip. The slip length typically follows an exponential temperature dependence, where EA is an activation energy and KB is Boltzmann's constant. For water on hydrophobic surfaces, activation energies typically range from 0.1 to 0.5 electron volts. Over a temperature range from 20 to 80 degrees Celsius, slip lengths can easily double or triple, significantly affecting device performance. How do scientists actually measure these tiny slip lengths? It's a challenging experimental problem. The most common method is to measure the flow rate through nanochannels under known pressure gradients, then compare to theoretical predictions. By measuring how much fluid flows through a channel under a specific pressure difference, we can back-calculate the slip length. Surface force apparatus can measure forces between surfaces separated by nanometer gaps, revealing slip-through drainage rate measurements. Atomic force microscopy can drag a probe through confined fluid and measure drag forces, which depends sensitively on slip. A major challenge is that slip length is extremely sensitive to surface preparation, contamination, and even dissolved gases. Computer simulations at the molecular level have provided deep insights into slip mechanisms. Molecular dynamic simulations track individual molecules, revealing the microscopic origin of slip at surfaces. These simulations reveal a depletion layer near hydrophobic walls where fluid density is lower, facilitating slip. The hydrogen bond network of water is disrupted at interfaces, reducing friction compared to bulk fluid. Simulations confirm that slip length is inversely proportional to the strength of wall fluid interactions. Let's directly compare how the same fluid behaves in macroscopic versus nanoscopic channels. Consider a millimeter scale channel on the left versus a 50 nanometer channel on the right, with the same slip length of 20 nanometers. For the macro channel, the ratio B over H equals 20 nanometers over 1 million nanometers, which is only 0.00002. The flow enhancement is 1 plus 6 times that tiny number, giving 1.00012, essentially no effect at all. For the nanochannel, B over H equals 20 over 50, which is 0.4, a huge fraction. The enhancement is 1 plus 6 times 0.4, giving 3.4. The flow more than triples. Let's use an everyday analogy to understand slip at surfaces. Think of ice skating. The skate blade doesn't stick to the ice, but glides over a thin water layer, creating slip. Ice skating works because there's a large effective slip length between the blade and ice, dramatically reducing friction. In contrast, walking on rubber involves tiny slip, which is why rubber soles provide good traction. Nanochannels with hydrophobic walls are like microscopic ice rinks, where water molecules glide along the surface. Scientists can engineer surfaces to control slip, opening exciting possibilities. Applying hydrophobic coatings like fluoropolymers can increase slip length by a factor of 10 or more. Carefully designed roughness patterns can trap air or vapor, creating superhydrophobic surfaces with enormous effective slip. The effective slip length equals the intrinsic material slip plus a contribution from surface roughness geometry. The lotus leaf effect, with its hierarchical roughness, can achieve effective slip lengths exceeding 10 micrometers. The Reynolds number, which characterizes flow regime, behaves differently at the nanoscale. The Reynolds number equals density times velocity times channel height divided by viscosity. It determines whether flow is laminar or turbulent. For a typical nanochannel, 50 nanometers tall with flow speed 1 millimeter per second. The Reynolds number is about 5 times 10 to the minus 5, incredibly small. This means flow is always perfectly laminar in nanochannels. Turbulence is physically impossible at these scales. However, slip effectively increases the Reynolds number because fluid moves faster than classical theory predicts. Where does energy go in these flows, and how does slip affect dissipation? Power dissipated equals flow rate times pressure drop. This is the energy lost to friction per unit time. For classical no-slip flow, power dissipation has this form, proportional to pressure drop squared. With slip, achieving the same flow rate requires a smaller pressure drop because friction is reduced. The power dissipation with slip equals the classical power divided by 1 plus 6b over h. Slip reduces energy loss. With our standard example parameters, energy dissipation is reduced by 70% compared to the no-slip case. How quickly do these flows respond? And what are the relevant timescales? The characteristic time for momentum to diffuse across the channel is h squared over kinematic viscosity nu. For a 50 nanometer channel filled with water where nu is 10 to the minus 6, the diffusion time is 2.5 nanoseconds. The flow reaches steady state almost instantly. Interestingly, slip doesn't dramatically alter this diffusion time. The rapid response is a consequence of the small length scale. Let's design a practical nanochannel device accounting for slip effects. Suppose we want to deliver 1 microliter per minute through an array of parallel nanochannels. Each channel is 50 nanometers tall, 1 micrometer wide, and 10 micrometers long. We have 1 atmosphere, or 100 kilopascals, of pressure available to drive the flow. Water viscosity is 0.001 pascal seconds. The flow rate per channel is given by this modified Poiseuille equation, including the slip enhancement factor. Without slip, each channel delivers 2.08 times 10 to the minus 16 cubic meters per second. With 20 nanometer slip, each channel delivers 7.08 times 10 to the minus 16 cubic meters per second, over 3 times more. To achieve our target flow rate of 1 microliter per minute, we need 23,600 channels with slip versus 80,000 without slip. Let's summarize this paradigm shift in our understanding of fluid flow. The classical no-slip boundary condition, valid for centuries of fluid mechanics, breaks down when channels shrink below about 100 nanometers. The slip length, typically 10 to 100 nanometers, becomes the crucial parameter determining flow behavior. Flow enhancement scales as 1 plus 6 times the ratio of slip length to channel height, making slip increasingly important in smaller channels. Friction is reduced by the factor h over h plus 2b, enabling more efficient transport with less energy dissipation. These effects have profound implications for drug delivery, water desalination, lab-on-chip diagnostics, and energy applications. These three master equations capture the essence of slip and nanochannels: the slip boundary condition, flow enhancement, and friction reduction. As we engineer devices at ever smaller scales, understanding and exploiting slip phenomena becomes absolutely essential for accurate predictions and optimal designs.